Sure.
Okay, should we get started then? I think we've got, I let everyone in. So, okay. So thank you everyone for tuning in to another Risk Institute online session. Today we're fortunate to have with us the Professor Dalal Alrajeh, who will talk to us about research on handling risks to goal assurances in adaptive systems. The presentation will be around 45 minutes and 20 minutes of a Q&A session. So please could you make sure your microphones are muted. And if you'd like to leave any questions in the chat, feel free to do so. So before we begin, I'd like to make a few announcements. So here is some schedules for the future talks happening in the next few weeks. So next week, as I mentioned last time, we will have Dr. Sylvia Tolo. This will be a hybrid event, so it will be nice to see some of you in person. She's giving us a talk about the current challenges and future solutions for systems safety analysis. So that's the 5th of July at 2 p.m. And in the following week, on the 13th of July, 2 p.m., we'll have Dr. Christian Schilling, who is going to give us a talk about a general introduction to reactability analysis for the dynamical systems. And on the 19th of July, we'll have Mr. David Ropaik, who will give us a talk about risk communication. It's not just about that fact. So I'll give you a little bit of introduction of today's speaker, Professor Dalal Alrajeh. So she is a senior lecturer or associate professor at the Department of Computing at the Imperial College London. And she currently serves as the Director of Postgraduate Research at the department. She holds a PhD in distributed software engineering from Imperial College. Her research is in the area of formal software engineering and symbolic AI, with a focus on specification learning. Specification learning, synthesis, and analysis of provably correct software systems. She is the recipient of several funding awards for her research, more recently for the current design of humans in the loop and AI-enabled systems for safety critical applications. She was a recipient of the Imperial College Research Fellowship Award, and she has served on numerous program committees of the premier conferences in her field, including ICSE, EFEC, FCE, SE, IJCAI and AAAI. So I'm going to just pass on to Dalal. So whenever you're ready.
Sorry, as usual, tend to forget that you the mute. So let me just share my screen. Yeah, does that look okay on your slide?
Yeah, it's perfect.
Yeah, fantastic. All right, thank you all very much for the invitation. Really delighted to be with you today, talking about some of the work that that I've been looking into over kind of recent years, particularly. So today I've tried to really try to bring it as much as possible to hopefully a general audience. If there are any questions, particularly or things that have not been clear, please do ask. I would say kind of major questions towards the end, just to make sure I get through stuff. But as I said, I'm very, very delighted to be here. So the work that I'm going to focus on is particularly on handling risks to goal assurances. Very kind of aware of using the word risks when I'm talking to the Institute for Risk and Uncertainty. So I will obviously mention what we mean by that, or at least talk about in terms of software design. I do want to give maybe a general introduction about the background of kind of the research areas and kind of methods that I work on and develop in my area before going to the particular problem that we'll kind of discuss today. So, I mean, typically when it comes to software design, there's an often interest or sort of a balance, particularly where we want to try to bring in rigor in terms of the way that we design our systems in such a way that's provably correct, and we can assure that it will, but however it will behave safely, but also in a sense make use of human in the loop, in the sense that we want to keep humans insight and overlooking over these systems, especially as we move towards increasing use of AI and machine learning in our software design. So we rely on these software systems to achieve ever increasing kind of challenging tasks. And we still yet want to maintain those assurances and those guarantees about the functionality and the impact, whether that's desirable or undesirable. But as these software get really complex, that role of the human insight in the development process itself or control when it's used during runtime becomes even more critical and challenging, as we need to make these proofs assured even in the face of unanticipated events. So that means somehow we need to still maintain that rigor in the techniques, keep the human in the loop, both, and have that rigor both in a sense in the development and during the use time. And there are lots of incidents where we have that combination, but yet we've not been able to really have a satisfactory way of achieving this. So where I focus on in terms of methodology is so my kind of centered in terms of research is often in software design, as has been mentioned initially, particularly when it comes to specifications. So these are ways in which we express what the software should do in a formal, in a logic kind of language where we can then write these proofs about them. But when we look at the software design, the idea often is that that human is going to provide us with some properties which the system needs to satisfy, and also sort of give us insight or build these models. What we talk about often is like mathematical models of behavior, in which describe how the system is going to behave or expected to behave at some form of abstract level. And we have these techniques, which are typically called verification techniques. These can be model checking, through SAT solving, etc., which can help assist us check that the behavior which we expect the system to do doesn't actually meet the properties that we want them to achieve, or the requirements that we want them to achieve. So human is still central to that, because in a sense, if it turns out these models don't satisfy the properties, then we want the human to be able to either potentially modify the properties or tell us what was wrong about the behavior. Because these verification, for example, techniques can tell us, okay, actually the model doesn't satisfy the property in this particular execution, but then there's a question, well, why it wasn't. So still humans are central to the explanation of those. So where I tend to focus on in terms of designing and developing theories and techniques to make sure that those properties that the humans initially provide meet certain assurance guarantees. So these could be in terms of their quality or their completeness or their consistency. I'm also really interested in some of my work is kind of focused on, well, if we find these problems in the models where the properties we're happy, we're satisfied with the properties, but the models are not what we expect them to do because they cover some behavior that we are not happy with or shouldn't happen or unsafe, is how to automatically elaborate these models, whether through some refinements or revision processes. But also some of my work is kind of how to automatically move from these properties to the models, sometimes even without having the human in the loop or changing the role of the human in the loop. But still within that process, as I said, kind of many of these applications or the areas which I'm interested in do still require the human at some point to check, even if we revise the models or if we revise the properties, are they still satisfied with that? And so there's always a question which I'm interested in terms of, yes, we sometimes need humans to augment our properties or augment our tools with some additional information, or in a sense to help us through the correction process. So that's kind of the sort of problems that I'm really interested in. And the techniques that I work on and develop are either focused on what we call formal inductive synthesis techniques. And these are techniques, for example, from learning from examples of symbolic learning techniques, for example, and logic-based learning being an example of methods that fall under that. But also more recently been working on aspects of causal reasoning. So in a sense, if we have different human experts or different, let's say software engineers or analysts who think the causes of failure, they might, or the explanations for that might differ, how we can combine their opinion about that, etc. So that's kind of generally, let's say, as a background to what I'm interested in. What I want to focus today is on a particular technique or method, which is on property assurances using symbolic learning and have these particular elements. And the particular problem is on adapting requirements model to varying environments. The main principle, let's say, is that we often, when we're designing software, we're designing it to operate in a particular environment, and these environments undoubtedly can change over time. And the question about how to, acquiring, let's say, full knowledge of the environments in which they're going to operate is not always available at design time, especially if we assume, as we know, we've got a dynamic environment, we have unanticipated events that might occur due to new services, new customers that might be using the software, new regulations, policies, standards, etc. So even when we design the software, we need to be able to anticipate these, that it is going to change, its requirements going to change, its environment's going to change. So how do we make sure that we can have software that can cope with that in a safe way? So let's take for an example, I'll take as a simple instance of designing an urban traffic control system for enforcing low emission zones. And often these are designed for environments where polluting vehicles like buses or lorries, etc., are generally present. And in some cases, it's also if you've got different types of vehicles, cars, motorcycles, etc. But the way that the low emission zone is enforced can vary, for example, from one city to another, but also from let's say one country to another, but also from one city to another. And you find that often what's very common is that vehicles with higher emissions might not enter the area, but more and for example, more polluting vehicles could have more charge if they do enter. So they could vary. They could vary in that instance, but they could also vary in terms of the penalties that these vehicles are issued if they do enter or don't follow the regulations in that sense. So if we look at, for example, let's say Brussels, and I'm going to focus on the London instance. So if you look at just, for example, London, which I think it changes so often, so I might have missed a couple here things there, but generally, let's say that polluting vehicles are admitted within certain, let's say, congestion charge, the low emission zones, but with charges, and these charges do depend on the vehicle type. Again, whether that's a motor, for example, certain charge, or whether that's a bus, a certain charge. But also, if you do fail, so if you do enter and failure to pay that charge would also depend on, for example, the vehicle type, and it could also be based on the time that's been elapsed as well since the offence had occurred, to put it that way. But if you look at Brussels, for example, at the time, at least when we initially, at least the case study that we looked at, which was back in 2018, at that point, polluting vehicles weren't admitted in certain areas in the city centre at all altogether. But also what we found is that if they do enter, which is, again, they will be issued with a fine, and that depends on the fuel type, whether that's diesel or petrol, the Euro standard, and if it's a repeated offence. Now, in that case, we need a software that, for example, I've designed it, I wanted to work into London, for the emission zone, but I wanted to be able to be useful and applicable to other contexts in this sense. Now, there have been a number of techniques that have been developed for adaptation, and you can typically group them into these three main kind of groups or categories of research, which is, requirements adaptation, where the idea there is still you have the rigor, you can have formal proofs in terms of trying to, or templates to be able to how to derive adaptations from original model. But these are kind of restricted to certain classes of the language that we express, or the kinds of adaptation, or sometimes they're actually, you've got the templates, but in a sense how general they are is often an issue. There's an area of dynamic software product lines, but these typically expect, similarly with the requirements of evolution, they often require that everything is actually pre-specified. So you kind of imagine what the different environments that it might operate, and you just shift from one to the other based on the trigger for certain context or conditions. So what we wanted to do in this work particularly was come up with a formal approach for the requirements adaptation, focus at design time, such that it's driven by satisfaction argument. And what I mean by that is that we have the same objective, let's say, in terms of the same requirement generally of these systems, whether that's for London or for Brussels. So that high level, let's say, requirement is still maintained, but the way that it's implemented or the way that we achieve that will differ depending on the context. So we want a way where we can look at in the logic sense of these satisfaction arguments, which I'll explain slightly a bit more. And we want it in such a way that only adaptations happen locally. So it's only made to what's needed in a sense. We want to preserve as much of our requirements or specification and just change what's required in a way where we can also identify automatically, for example, the different ways of anticipated events that might occur given the context that we imagine it will be operating in, or the environment. We want it in such a way that there's, learning process, so the human doesn't require, having some automatic machinery to be able to achieve that. And in such a way that if we do generate these requirements or these specifications for the new context, for the new environment, that we have this notion, often we're interested in software engineering, which is implementable. So there's no benefit in being able to have requirements that you're just never going to be able to specify or implement a software that could be that can implement it. By implementation here, we often look at what are the different components that we have, what can they monitor, what can they control, and that's where the implementation concerns come into play. So just to give things a bit more context. So when we talk about requirements, typically at a high level, we can structure these diagrammatically in these kind of tree-like models using certain frameworks that we do exist in software engineering, which enables essentially the formal specification and analysis. So just for the purpose of illustrating the method in a sense, I just want to go through an example of these models. So what we have is what we call these general, say these top level goals or requirements. Like this case, for example, with urban, I want to be able to, for any software that I'm going to implement for this purpose, I want to be able to the urban traffic death toll to be reduced, and that could be, for example, through these typically high level goals are then refined. So that's achieved through enforcing some low emission zones to reduce traffic, but obviously we've got different purposes. So there could be multiple high level goals, for example, like reducing pollution, etc., more generally. And then speed limit enforcement. And then you can imagine that you just go through this low level, you refine these high level goals until you reach what we call as leaf goals. And these are things that you can actually assign, say, okay, that particular software component is going to be responsible, for example, for setting the fines if it detects what vehicle is entered the area and what typical offense type those occurred. Or you can assign them to agents in the environment and say, assuming the environment does this, then I know that my software can achieve that high level goal, given if it meets this particular specification. So we have the goal, typically these requirements, for example, I've highlighted them here in blue, and what we have to be able to achieve these requirements or environment conditions. So you basically describe in some form of logic what properties the environments have, and I'll give examples of that just to make it a bit clearer. So imagine now I've got my model for the London context, and basically what I want to be able to do essentially is from this model automatically transform into a model that would be correct for the Brussels context, essentially. And that's the question is, how can I go from the original model to something like this, where the semantics of these models are preserved. The idea is that any leaf goals have to provably satisfy the top goals. There's notions of minimality, consistency, etc. So there are a lot of properties that these models have underlying in terms of the logic sense. And the question is, how do we go through that in an automatic way while preserving these guarantees? So in this work, we developed a framework or an approach, RESPIRE, for requirements, adaptation, varying environments, which have three main components, essentially. The idea is that we build initially phase one, let's say, a reference model, essentially. So if I have, let's say, my London model, then I have my Brussels context, environment conditions that I know, and I have agents components that I have, and these are the things that they can monitor, and these are the things that they can control, essentially. Then from there, we essentially take that model, and then we have the core part of it, which is, the core part of it, which is what we call the kind of counterexample guided aspect, where you automatically check the model for properties of completeness, consistency. If it turns out that it's not, then you learn a revision to these models, etc., until finally you come up with this new model at the end. And in such a way that you make sure we just do a small minimization process where we remove any goals that are not needed to achieve the high level goals in an iterative way. I mean, and I'll talk you through the different processes of these to show you essentially how this works. So let's take in this case, we assume, at least, again, this is kind of being central in terms of the human part of it, is we assume that original model that I showed you, a human will pick, saying at some point, this is the highest level goal, which I want to preserve. And anything below that is up for modification and adaptation. I'm not really, as a human, I'm not really sure which ones, but I just think this is the one that I definitely have agreed I want to preserve it in this new environment. We call this top goal, or top requirement, an anchor. So for example, it might be something like expressed in some form of logic, but semantically meaning, let's say, it's always, if the vehicle is polluting, then it's penalized. And then we have, let's say, in our reference model, so the only goals that I had, requirements that I had at that point, is the London one. So these are the ones that I know the software that I currently had was designed for. So an example of this could be, is always if it's a lorry or a bus and the Euro category is below 3, then it must be penalized. And then, so this is already, as I said, how the current software operates. But what I do know is now I've got my new environment, which I want the software to be able to operate in safely. So I would plug that into my specification or goal model. And in this case, for example, might be something like, if it's polluting, then it's not admitted. Now, the challenge here is I've got my anchor goal, I've got my environment conditions, I have my old requirements for the previous software. How do I suddenly fix this model so that it is complete, consistent, minimal, etc., for this new environment? And I have preserved my guarantees. So this is where it comes to this counterexample guided learning process. And this is something that I've been, working over for different years, a general framework for basically tackling issues to do with the quality of specifications. I've kind of often spoke about completeness, consistencies, etc. But this is something which is often applicable to many different types of logics, applicable to different problems, types of types of systems, reactive systems, etc. So what's the idea behind this kind of framework of approaches of counterexample guided learning? The idea, again, even within that, it's the human is central to that, where you typically have two interactive methods, let's say, that help us come up automatically with specifications. You have an inductive synthesizer, and that could be like a symbolic learner. Again, I'll touch upon that in a short while, where you can give it examples, whether that's examples of behavior from the human, let's say at the top, and then what the inductive synthesizer, you give it, for example, saying, this is the language in which I want to I want to express my specification, and the inductive synthesizer automatically generates a candidate specification saying, from this behavior that you've provided me, I think this is a candidate specification that that covers the behavior that you want, plus any other constraints that you might have expressed as well. And then, but we want to make sure that that candidate specification actually meets certain guarantees. So, like I've said in the beginning of the talk, interest building, models of stuff, and you building your properties and checking against these properties. The idea is that you can query some form of verifier, whether that's a model checker or a SAT solver, saying, is this the candidate spec that you wanted? And this verifier or this oracle would come back and say, no, it's not good, because it actually covers or allows this behavior, which your software shouldn't really allow. And so the inductive synthesizer might then say, okay, now generate a new candidate, and you can have, and it can then be queried to check whether it does meet it does meet the necessary, let's say, properties that have been specified. Now, this sort of framework has been applied, and sorry, it's been developed for different, let's say, areas, whether that's within software engineering or within formal methods. But kind of our focus has been, how do we make such a framework really work for problems to do with specification quality? And so part of the here was really looking at an application of it or a modification of this to be able to solve the problem of requirements adaptation. So to go back to the problem in terms of the counterexample guided learning. So as I said, I've got now this reference model, and I want to be able to automatically generate now a full, complete, consistent model for this new environment to which I want to apply the software. So to trigger the adaptation, what the method does is it takes these leaf goals. So these leaf goals are these, as I said, these are the requirements that are going to be assigned to the different components of the software. It takes the current so it takes the sub goals of these for the example for the London context initially. It takes the environment conditions for the Brussels, which is the new environment in which it's going to be deployed, and it checks, does these goals that are already part of my model actually meet this high level anchor goal in this new environment? If the answer to that is if the answer to that is no, what you get is an example that shows why your current software as is in the new environment won't achieve that high level goal. And so that's an important example for us to demonstrate where failure occurs. And that's again something that, whether that's human inspect, a human can inspect in that sense to see and understand the reason for failure in that particular environment. So that's something to trigger on that essentially just tells us, okay, your model is not going to operate safely or correctly within this new environment. But the space for adaptation, as I mentioned before, could be very large, and we want to avoid having to pre-specify all the different ways in which we can adapt the software. So to guide that automatically, what our framework or what the method does is automatically do the check of saying, well, is there in a sense, what are the different conditions, let's say, in which our anchor goal, so our original one in the environment case, doesn't satisfy our leaf goals. And what this allows us, in a way, it gives us examples potentially of how we could achieve this anchor goals. It's kind of notions of satisfiability, saying actually these anchor goals with the environment conditions are achievable essentially, but not fully in a sense. But these examples could essentially highlight how they could be achieved. And this is again a point where we generate these automatically, but again, a human can inspect and be able to modify if it doesn't seem applicable or appropriate. And so we use that as an example of anchor satisfiability. So what we come up with at least is now two examples, one of why the current software doesn't operate in the new environment correctly, and in a way in which here's an example of how it could potentially operate safely. And now what we do is then, and maybe, sorry, just to say this is a specific instance, let's say, for this particular example. So what I might give as my leaf goals here is saying, if I give my specification for the vehicle type being charged and the fine set and according to London plus the environment condition, does that entail, or does the behavior induced by that always satisfy my anchor goal, being the polluting vehicle penalized? And in this case, what we do find is that actually it does need an adaptation, because a lorry that's running on diesel enters, the behavior induced by the London system allows a lorry running on diesel to enter the low emission zone, and it's not find an issue. Or not given a penalty for entering that. So that tells us there's a problem with the model, but there's a question that remains is where exactly in that model or my requirements is the problem? Question of how do we resolve it in a correct way? Do we rewrite the specification as a whole? Do we change the refinement relationship? For example, in a sense, maybe I'm relying on certain requirements like I don't know, in this model, fine set by vehicle and offense type right at the bottom. Do I change the kind of refinement process that we have. So there's a lot of question where it's not obvious just by looking at the example, where exactly in my model can I change? We also don't want to make such minimal changes that you keep on changing it and it becomes just as laborious as rewriting a whole model. So we want to be able to, from very few instances and examples, to be able to in very few steps as well, to modify this model to a correct, consistent, complete, etc. One. So these are the questions that typically that we need to consider, or the method needs to consider automatically. So it's not kind of obvious how to do this in a correct way. And so the underlying engine that we utilize and build on and have extended essentially is a method under what we call logic-based learning. So what it is logic-based learning is a computational mechanism to inductively synthesize, revise logic programs from observations of what's true and false in the models captured by our program. Typically, these contain different components. So you have a background theory. So these are things that you know that are true about the world in a sense, and the expert or the design engineer or the software engineer could have informed you by physics of the world, things that can't happen at the same time, or etc. You have a revisable theory, and these are parts of your logic which you think are potentially up for adaptation or change or revision in a sense. And the idea is that your current background knowledge with this revisable theory don't explain some of the observations that you have about the world essentially. And so what we want to be able, what the method is sent to do is try to then focus its modification on inducing or generating a revised theory such that this entailment coverage relationship is restored. What we do as in terms of logic-based learning is we can describe what we call as like a language bias. So we can say, for example, this revisable theory, you can revise it using this part of the logic signature, and which we define through language, what we call the language bias. And you can also provide structural constraints, saying, for example, in a sense, I don't want these things to appear in my solution space. So we can have control about what the solution space could look like from which we induce these different solutions. But also what we have is we can specify optimization objectives over cost. So we can, the typical standard cost computation is essentially is minimizing the number of changes that need to be made to the current theory to obtain the new one. But you can also have user-specified constraints over the cost, in a sense, saying, how much coming, if you replace a particular, I don't know, part of your expression, I don't know, if I change polluting to penalize, for example, that will be very costly, for example, compared to something else. So we can express these things to inform our revision. So as I said, we utilize logic-based learning to help us derive these adaptations, and by essentially using the semantics of our goal model, the environment conditions that we have, our agent spec, the anchor goal, the high-level goal that we want to satisfy, all as part of our background theory, because we're saying we don't want to change any of that. That part of our model is going to be fixed. And what we put in the revisable theory, we put the bits that we think are, we're allowing changes to occur to that. And that will be the goal specification that we have, with the requirement specification we have, the different types of refinement relationships that we express. We'll plug that into something that's revisable. And we give essentially those examples of the anchor satisfiability trace and the violation trace that I demonstrated earlier as examples for the observation. And we just specify our adaptation space to be all the goal specifications that we can express with a given strict signature and the refinement relationship that we can allow, that we would allow. And the focus here is saying, by the logic-based learning, saying just finds those minimal changes to the spec and the refinement relationship that would allow the coverage, essentially. So the optimization objectives we specify in this case are partly to do with syntactic similarities, so saying for the logic expressions that I have initially, I want to focus only on those that can be derived from the existing spec with very few changes to the signature. That doesn't mean that we won't allow a lot, but instead we give preference to as few as possible changes to the specification, under the assumption that typically when we write these specs, we tend them to be general. We want to preserve as much of them as possible in a new environment. But also what we want to do is, as I said, we want to localize the changes. So even in terms of our refinement model, saying focus on changes that are as close as possible in terms of the number of refinement links that you have, rather than trying to change across the whole goal model in this case. So we want to really localize that as much as possible. So going back to the example that we had, so the learning generates a candidate adaptation, which issues a fine for any vehicle running on petrol that enters the area. And so what the RESPIRE method does, it checks now, okay, so now for this new, I've revised these two specifications, and the learners found this automatically. And so what RESPIRE does, it checks the sleeve goal in the new model against the anchor goal that we had, and find that actually what it does, it still requires further adaptation. So it doesn't, it's not the case that we've managed to restore this entailment relationship. And so again, the learner would generate a new spec for fine set by fuel and offense type. And we say, well, is this model fine? Does it meet and satisfy the anchor goals that we have? And actually, in the case it didn't, for example, we don't need to trigger, we didn't need to trigger an adaptation because in fact, it does meet our anchor goal. And because our reliance and the way that we formalize logic-based learning, we've actually guaranteed by soundness of our method, the completeness and consistency of this model within few steps. Obviously, this is a very small example, but there's a point about being learning from example and generalization allows us to automatically do these adaptations in very few steps. So in terms of the minimization, we've applied standard techniques from actually software tests to try to come up with the smallest, just check that actually, are there any goals that weren't necessary within that goal model to achieve? And then we drop those. And then based on that, we check, are there any other anchor goals that are needed to be met? And then the process also continues. So there's a process, there's a loop essentially needed to generate an adaptation for a particular anchor goal, but you might have several anchor goals in your model, and so we might need to loop over those essentially. Now, to evaluate the method experimentally, we built a prototype in Python, which was built on model checking SMVs and a learning algorithm which we've developed in the department. The tool keeps the engineer in terms of validating the choice of the anchor goal and the satisfiability traces for adaptation. What we did is we considered 6 variants for a computer-aided dispatch, an ambulance dispatch system. I think there's something in the chat that popped up, but I can't open it, I think. So if there's anything that needs to be said, or that I'm running on time, yeah, I should be done very soon. So yeah, there's 6 variants. We looked at 2 contexts for the ambulance dispatch system, and Belgium, looking at both directions. And the focus on our case study was really looking at the different kind of picking cases of specification where we needed to test these different adaptation strategies that I've talked about or mentioned, whether that's the different refinement or different kinds of specs that are needed. And it gave us really first insight in terms of how we can achieve these automated goal model adaptation at design time without having to fully pre-specify the adaptation space. Essentially, yeah, I mean, in a sense, I'll probably kind of go through this very briefly, but I mean, again, we've tested it on the both ways. We've been able to, in very few iterations, bearing in mind that the complex specifications that we had, although the goals sometimes they're required, I mean, they had sometimes up to 10, 15 goals expressions which are really complex, and actually if you've even rewrite them in forms that then the numbers of those could increase up to 40 sometimes. But actually, in many of those cases, the adaptations just required very, very minimal changes, and in very few iterations, we were able to achieve the required completeness and consistency guarantees. Yeah, I mean, sorry, probably just bearing in mind time for questions. So yes, so essentially we looked at the number of goals that we needed to be learned, the number of goals that we had, the minimization step, the number of iterations, the different types that were required in terms of refinement, and how much it took in terms of time. So in the graph at the below, the y-axis just tells you how much time we had in seconds, and the average cost essentially per adaptation, per complete adaptation phase that was required for that. Okay. So in terms of this requirement adaptation, we would focus on, as I said, the key thing was being driven by kind of proofs of satisfaction arguments, not having to explicitly define the whole adaptation space a priori, focusing on local and similar adaptations, and looking at, in a sense, how we can use this counterexample guided learning by guiding learning through user-defined quantitative objectives. But this was all good, you know, for design time. You know, there's still a question, but what if you put the software in at runtime and now changes happen at runtime? So we're looking at ways in which we can integrate a controller synthesis with notions of system degradation. So there is that you realize the environment, you make assumptions about the environment, and actually those assumptions about, let's say, the Brussels environment are no longer true. So how can we use that information to potentially, let's say, degrade the software, in a sense we allow the software to operate still, having some guarantees, but weaker than what we had before, but also how we prioritize the different kinds of unanticipated events. And that's typically what we refer to in terms of the risk when it comes to the design. So at the moment, any violation is treated equally, but there's a question about actually which ones should we prioritize and focus on. But a key question, and this is probably what I kind of pushed the sport forward in a sense, is great, we were able to adapt these requirement models, but then the question is, our learning itself, sometimes what we've discovered in our learning, that the question, you know, we have to set the parameters for learning. So I have to say, though I don't give it a fully pre-specified adaptation space, there's a question about the parameters I give to the learning. So obviously if I change the parameters, sometimes I might make the solution space very large, or the candidate solution space very large, and sometimes if I reduce it, then I might not find the solution that's anticipated. So obviously that still remains a very strong factor, particularly if you want to enable runtime adaptation. So then the question comes, well, you know, we're adapting specification, but maybe what we really need to also to enable this runtime is adapt the learners themselves. So very briefly, I'm not going to spend much time on this. What we looked at essentially is work that says, you know, how can we adapt these specification learners such at runtime? So I need to be able, I'm going to design my software. I know that I can't anticipate everything, and I want to be able to explore the solution space in different ways at runtime. So again, going back to this underlying kind of framework in terms of having this counterexample guided learning aspect. So we developed kind of recently an approach to you give your specification, you have what we call this configuration learner, which tests different parameters of the learning. It then gives those parameters to the specification learner. The learner then tries to come up with the specification. We have a model that checks the quality. Is it implementable? Is it not? So what really that's testing is saying, given those parameters that you gave me, did you find a good quality specification or not? And if it didn't, we use that as an example to then reconfigure the learner. So what you come up in the end, we kind of designed it with a reinforcement learner. What it in the end learned is a configuration policy. And the idea is that this configuration policy, when it comes to runtime, you would equip your controller, your software controller, with an adaptation, equipped with an adaptive learning capabilities that can monitor the satisfaction of environment assumptions. And then, you know, just for example, I won't talk about this too much, but suppose you've got this forklift, which has to move boxes from one location to the other. You have your initial specification. In this case, I'm just talking about how it might operate at runtime. you observe in the environment that actually one of the assumptions you had in the environment doesn't hold, was violated. So you give it to an adaptive specification learner, which using the policy that was learned, looks at features of the current assumptions or the current goals that you have, and says, given this and given the violation that you had, this is the configuration that you need to give your this is the configuration you give to the learner. The learner come up with the specification, give it to a synthesizer, which generates automatically an implementation, which you can then enact. And that's kind of where mainly recent focus of mine has been on. But there's different directions interested in, particularly when it comes to that, is, to learn these policies, we need to think about mutating specifications to be able to test the space of what's good configurations and what's not. We need to come up with features about the specifications. We need to be able to evaluate the learning outcomes. At the moment, we look at implementability, we look at notions of how weak our specifications are. We focus on particular group parameters. We didn't really expand to all parameters that we could potentially consider, and also going through proofs of correctness for our learners. And also in terms of actually, we want to be able to evaluate it at a runtime in terms of the metrics that we might want to utilize to be able to determine how good the policy was, and also in terms of what the impact of different configurations are. So we want to think about a few metrics around that, and also just at the moment, at least for runtime, we're considering, let's just drop the human in the loop for the moment. But actually, if we do need to do that, how do we integrate that process? Just to finish off here, I just want to thank a lot of collaborators who contributed to different elements of this work, Advan and Axel, both in terms of the first on design at design time, and Sebastian, Jeff, and Alessandra more on kind of either the learning or at runtime, and Patrick as well on that runtime work. And I'll stop there. And please open to questions if you have any.
Thank you, Dalal, for very insightful talk. I think we've got some time for the questions, and I see someone raised hand. Do you want to unmute and ask a question?
Thank you so much, Carrie, and good afternoon, Professor Dalal. So thank you so much for your presentation this afternoon. It's really interesting work that you've shown. It might be a bit of a naive question over here. I might have missed this out, but do you happen to able to share with us, what is the potential extension of this work, somewhere for the future that you plan to is there any plans to extend this work towards other contexts and other other form of studies in the near future?
Well, I mean, so in terms of so much of the work example now we're really, working on at the moment is the idea, as I mentioned, is kind of system degradation. So this is when, if you design your software, let's say you've got your UAV or your drone that's operating in a particular environment, and then suddenly, you hit some unanticipated event. That could be something that you didn't factor in the design of the operation of that particular drone in that case. Then the idea is how to safely adapt its implementation at runtime in such a way that you allow it at least to achieve maybe either it can just modify the assumptions that have the environment while still trying to achieve that same objective, or in a sense saying, well, actually, I'm going to try to achieve a weaker objective. I might not be able to reach to suppose, this is going to be probably a bit of a naive example, but say, for example, it could be that you need to achieve, the goal is to reach a certain point of a drop-off point, but for some reason it wasn't able to reach that. Then you have an intermediate goal that you say, I'm going to adapt it and do this for now, and then I might delay the time through which I need to achieve the higher level goal. So that's really where we're working on, but also in a sense improving the learning algorithms. A lot of focus at the moment is saying how to improve the learning algorithms to actually generate when it picks its first candidate specification. There's a lot in terms of that candidate specification it generates does influence very much how many checks we have to do and the complexity that we're looking at. In the sense, we want to be able to reduce the number of checks for verification. So there's a lot of work under that we're focusing on as well.
Right. Yeah, thank you so much for your clarifications. And I'll just leave the question to my colleague who's waiting. Thank you so much once again.
No, thank you for asking. Thank you.
Yes, no worries.
Enrique?
Hi, yeah, just a quick question.
Sure.
From an ethical perspective, can you comment about possible negative impacts of this work?
Say that again, from an ethical perspective, how?
Yeah, can you comment about possible negative impacts of this work, like using formal logic to decide whether to find a car or not, and that sort of stuff?
So, I mean, what we're trying to do in a way is, I think that's kind of the move, at least the moment, saying, can we prove guarantees? And again, you know, in a way where at least we have some assurances about how things will operate. Of course, what's going to happen is, depending on what you express, let's say, your initial assurances that you want to meet, if those are incomplete, or I mean, the end of, you know, in the first instance, we assume properties have to come from somewhere. And so humans going to provide at least some insight. And the idea, or at least the underlying assumption, is that human is going to give us some specification, and that is going to give us initial properties about the system, what it should operate. And that typically the kind of problems that these have are, let's say, mostly to do with consistency, completeness, minimality. But I think, you know, you mentioned the notion of kind of ethical. There's a question there which is really interesting, saying, well, how do we verify how ethical the specifications are? And if there's a way that we can check that and actually integrate that, then that'd be really interesting to look at how these counterexample-guided learning methods could actually help us if we can articulate that as a property that we want systems to hold or satisfy. So that's a very interesting point, and definitely would be interested to consider that.
Yeah, okay, thanks. And just a follow-up, how would exceptions be dealt with in this case? Because, well, yeah. I think that's
a very good question as well. So the question is, you know, in a sense, the way, at least, you know, maybe I understand the question, please do correct me if I'm wrong, but there's a question where sometimes it might have been in one instance, there's something that happened where, you know, there's a violation, but you don't want the whole thing to change just because it was an exceptional case. And that's absolutely a very valid point, which we're looking into at the moment. I still don't have an exact solution. So the question is, maybe we should just, you know, allow the system, the question is, I suppose we're thinking about, is what if you reach a point and now the software is stuck because it assumed, for example, that it could go straight, you know, the drone can fly ahead, but it can't because now suddenly there's some building at the point, or I mean, maybe or something there that's kind of prevented from being able to actually function. So there's a question about, okay, what we could do is just try to find potentially an alternative plan just to be executed without modifying the whole specification, or what do we do? So we've not yet considered exactly how that's dealt with, but any suggestions, definitely be interested to hear that.
okay. Thank you.
Thank you. Thanks for your question.
Anyone else that's got comment or answer for Dalal? Do you have a paper or a book chapter that we could potentially?
Yeah, I think I probably put just on probably if you go back to this, I mean, I just put under the title, I just put at the bottom the conference publication that work was published at.
Yeah.
So I had to send that as an email as well. That's
great. Yeah, it seems like there is huge potential for like a wide range of applications, like the one that you've presented in the application to the cities. How much time, effort, and money that could potentially be saved by? Oh, that's a good question. Because I assume that you'd have to like sell it to, like, you know, get funding. I mean, I wouldn't be able to put I wouldn't be able to put a number, but that's a good point in the sense that often it comes to, you know, again, maybe I go back to the point I was trying to say in the beginning. I mean, writing requirements, specification, the problem is that if you don't have them to be complete, you do hear about, you know, for example, I think one of the examples I had before about the I6, where, you know, these are things which, you know, 46 million, you know,
they're being spent, invested, and then often you look back and you see one of the problems to do with requirements and specifications. They were incomplete, they're unrealistic, they were designed for unexpected environments. So these are the kind of problems that one would tackle. Now there's an issue where it'd be great if we can get the specifications that actually were said in requirements, so we can test and apply and see actually how much we would have been able to identify these things. So we do try to get, for example, the London dispatch system, that was one of the systems where there are millions of lost of money on that, and so typically it's used as a benchmark to see what could we have done, could we have checked it automatically? And it comes up, with the cases, yes, you could have done it automatically. Now, we're talking about now, but a failure that's happened, quite a while ago. So it's against so that's kind of what we're striving to, saying actually could have we done, but I didn't put a number on in terms of this, how much exactly would have saved.
Yeah, thank you. If there is no more question or comment.
I have a technical one, but
Sure.
I thought Scott was going to ask this, but do you consider somehow uncertainty in the logical statements? So yeah, it's often the case that if you are using a camera to detect whether it's a bus or a car, that system would have some probabilistic prediction about that, and then how do you introduce that in the logical operations and so on?
So that's a very good question. So at the moment, we don't put probabilities about the occurrence of the event. We assume does it happen or not, and that's kind of one of the things I mentioned. Actually, it'd be really nice to extend to look at applications in terms of actually putting a likely putting some kind of whether likelihood or weight or probability in terms of the counterexamples that we do identify. We've extended now to the learning, so we've got now a very scalable kind of learning algorithm that does work in terms of learning probabilistically, but we've not yet applied and tested. So that's definitely one of the things where we would be interested to see is one is either in terms of the probabilities of those particular scenarios that we identify, their likelihood of occurring, but also in terms of the specification themselves. At the moment, we're saying if this happens, then this should happen, but we don't really even assert some, I wouldn't say probability in the sense of the spec, although there are ways in which you can express probability and specification, but I don't, at the moment, these are, let's say, kind of need to be satisfied in a clear cut sense, but we, it's extendable to do that, but we've not yet reached that point of doing it.
Yeah, so we recently have written a paper on extending Boolean operators to account for uncertainty. So you can do like and, or, and any other logic gate with uncertain inputs. So maybe that could be useful.
Yeah, please do send that. Yeah, I'd be very interested to read through that. Yeah.
Okay, yeah, I will do.
And I mean, there's a whole kind of area of probabilistic logic-based learning as well, which has kind of been, again, looking at expression of logic, but often it's saying, it's more of the formula that if this is true, then and this is true, then the probability of a consequent occurring is of that. That's kind of typically how these are expressed. Exactly okay, yeah, so then it might be a very similar area then. Yeah, absolutely. Be very interested. So please do send that to me.
I'm not entirely sure how to do that with more complicated arguments like modus ponens or any, this kind of sophisticated arguments, because we sort of applied to a fault tree analysis, which is just logic gates.
Yeah.
But if you can construct arguments using, I think it's possible. If you construct arguments using logic gates, then you should be able to propagate that uncertainty through the argument.
I see. No, I'll definitely, I'll definitely read and then come back to you in terms of what I see, kind of similarities or wheres of kind of applicability, etc. Yeah, so I'd be keen to look into that.
Could I interject a little bit? Thanks, Enrique, for bringing that up. I we had a fire here in the building yesterday, and they're still calling me to tell me about the balcony inside. It's I missed part of
Saw
your
the
talk.
fire.
Yeah, did you see it?
I mean, the fire trucks.
Very dramatic. Yeah, we were expelled from the building. It's a big mess. And I missed part of the talk, the presentation today, so I'm sure I'm coming in from left field. But there are, yeah, of course, you're aware that Carl Wagner and others have just showed how to do probabilistic modus ponens. So we know how to do that. But I'm wondering, there are lots of different ways to learn, right? So logical inference is one thing, and probabilized logical inference is another. But there's also the statistical approach. But you shy away from the statistical. Is that true, or have I missed that part?
No. So I said we didn't kind of go down statistical. I mean, so the kind of learning that we're looking at the moment, at least in terms of the logic-based learning, is that we want to be able to have, in a sense, the way that we preserve kind of logic semantics of what we have is, we want to be able to preserve logic semantics. So that's kind of one thing about what it means for something to be true, what is a derivable, etc. The other thing that we're quite keen on being able to achieve, which is maybe this is a statistical method, but I'm thinking more about kind of machine learning and statistical machine learning, is that typically you need lots of examples. And what we're focused on in terms of logic-based learning is that it typically is not, it's not data hungry, in the sense that it just really can operate from one example and come up with solutions. So we want to be able to have something which doesn't require many examples. And the other thing we wanted to preserve is the interpretability of the output as well, and the proofs in terms of how things were constructed. So we don't do, proofs that we have are not, they're not, let's say, kind of natural deduction proofs or that sort, and we deal with kind of methods to do which are much closer to the semantics that we have in terms of, I don't know, kind of answer set. I don't know if you kind of covered kind of answer set programming, where you can what is true or not tries to reflect, let's say, logic structures and how we determine truth values with respect to logic structures, etc. But that's not to say that it would be interesting as well to see actually how can we push and how could the statistical learning methods could be applicable, and what would be the requirements in the sense, both in terms of data and in terms of properties and in terms of the guarantees that we could ensure if we apply these in the kind of context that we are applying them.
Thanks very much. I'm going to ask you some more questions. I'm just not at the moment.
Okay, sure, absolutely.
It's quite interesting.
Yeah, no, I'll be keen to, again, thanks again really for the opportunity, and it's great to be able to virtually meet people there. And by all means, I'd be very keen to hear on any follow-ups or papers that you'd like to share, and hopefully, there's something there that we can work on.
Sure, cool, thanks.
All right, thank you very much.
Okay, yeah, thank you very much for again for that very insightful talk, and thank you everyone for commenting the questions. So hope to see you soon.
Same here. Thank you very much.
Thank you, everyone.
Take care. Bye.
Thank you so much.
Thanks.